So, good morning or good evening, wherever you are. Hola, bună ziua. I am Christian Maier from University of Vienna, from Department of Astrophysics, and I will talk about strangulation in a high redshift cluster revealed by enhanced metallicities and ALMA molecular gas. This work is based mainly on the paper published in 2019, a work done together with Masao Hayashi, Bodo Ziegler, and Teddy Kodama. So first, what do I mean by strangulation? In humans, death by strangulation is a slow process. The victim uses up oxygen in the lungs, but keeps producing carbon dioxide, which remains trapped in the body. So high levels of carbon dioxide in the blood of the corpse, when police is coming to see what happened, suggests strangulation or suffocation. In galaxies, strangulation is a slow star formation quenching process. If you look at this bathtub model here, the water in the bathtub is the gas. So the supply of pristine gas, which would otherwise dilute the ISM, on the galaxy disk is halted, but the star formation can continue using the gas available in the disk, because there's still water or gas in the disk, until it is completely used up. So instead of building carbon dioxide, like in humans, strangled galaxies accumulate metals produced by massive stars. And since there's no gas dilution of the ISM by the pristine gas inflow, so no water coming in the bathtub anymore, one gets higher metallicities. So these higher gas metallicities, like the carbon dioxide in the corpse, are evidence of galactic strangulation or suffocation. At lower redshifts, 2019, there were two papers showing that there is a slowed and rapid star formation quenching scenario. So what happens? The galaxies fly towards the center of the cluster. You can see here in this sketch. First, after passing the virial radius, R200, the slow quenching happens because you have a supply of pristine gas onto galaxy disk halted. And if you look at this diagram here, you can see that the density of ISM is increasing when the galaxy comes closer to the inner part of the cluster. This density was measured actually by Chandra X-ray data at low redshift. So you can see here the quench fraction of galaxies slowly increasing, and you have a slow quenching. And at above a threshold, the quench fraction of galaxies is increasing fast. So you have rapid quenching with the cold gas affected by room pressure. In our work, together with Bodo Ziegler, Chris Haynes, and Graham Smith, we looked at locus clusters and found a slowed and rapid quenching at redshift 0.15 to 0.26, revealed by higher metallicities inside R200, and by comparing the fractions of star-forming galaxies as a function of cluster-centric radius with simulations. We found quenching timescales of 1 to 2 gigayear for slow quenching using part of the available gas reservoir, and 0.5 to 1 gigayear for rapid quenching when the ISM density gets higher, so the round pressure is higher than the restoring pressure of the gas, so when the galaxies travel to the denser inner regions of the cluster. So this was in clusters at lower redshifts. But what happens now at redshift 1.5? Do we see also some strangulation there? For this study, I use this cluster, which I will name XMM2215 in the following, which was discovered in the XMM cluster survey. You can see here an HST H-band image with the spectroscopic cluster members at R less than half R200 shown. Then mass of this cluster is 6 times 10 to the 14 solar masses. It has extended emission from the hot gas, showing it is in an advanced evolutionary state. And the wealth of spectroscopic redshifts for classical galaxies are published. So one can do a Phasebased diagram and find out where this galaxy lie. I used KMOS spectroscopy of H alpha and 2 from the ESO archive, covering about R200 for 19 cluster galaxies, and I could measure oxygen abundances for 10 of them using N2H alpha. You can see here the table with the 19 galaxies, N2H alpha. The masses, these are quite massive galaxies, above 10 to the 10 solar masses. Most of them, the oxygen abundances, some are AGNs with high N2H alpha, and also the distance from the cluster center, R2, R200. Because what we did was to do a phase-based diagram. So you can see here the cluster-centric radius versus line of sight velocity, absolute value, relative to a cluster redshift. And this characterizes the accretion state of cluster galaxies relatively free from the effects due to the 2D projective positions with respect to the cluster center, shown here in the right panel. The phase-based diagram at R less than R200 was done using 58 cluster galaxies with spectroscopic redshifts. The dashed triangle here shows the virialized region derived by Rie et al. 2017 using cosmological hydrodynamic simulations of clusters. The galaxies with KMOS H-band spectroscopy are shown as large symbols. The red field symbol is the BCG. You can see here it is offset from the X-ray ray center. And infalling galaxies with KMOS spectroscopy are shown as blue stars. So the main result from the paper was the mass metallicity relation. Here on the left, you can see the oxygen abundance using N2, so N2H alpha, versus stellar mass. The slow relation is shown here in red with the 1 sigma scatter. The galaxies which were in the triangle here, so in the inner part of the cluster, are shown as triangles, and infalling galaxies are shown as stars, and the field galaxies from KMOS 3D survey at similar redshift are shown as field circles. The stacked values from KMOS 3D are shown as these field squares. So you can see that the galaxies in the inner part of the cluster show higher metallicities by about 0.1 dex compared to field galaxies and infalling galaxies. Looking now at the N2H alpha, you can see the same trend. The galaxies in the inner part of the cluster show 0.1 dex higher metallicities than the field galaxies from KMOS 3D and infalling galaxies. Additionally, these galaxies have slightly lower specific star formation rates. You can see here the SSFR versus mass relation compared to the O2 emitters in and around the 2215 cluster. So all these are O2 emitters from narrow bands. So you have still star-forming galaxies with lower SSFRs and high metallicities. So we deduce slow quenching. Strangulation is happening in these galaxies. The ALMA molecular gas was measured by Hayashi et al. And you can see here again a phase-based diagram, but without the absolute value. So that's why the triangle looks like that now, which was here. CO emission line detection was observed in several galaxies, shown in red, but some members were not observed with ALMA. From this, one can deduce that the main component of the stripped gas is the neutral gas, while the molecular gas from ALMA is less affected by the ramp pressure. So the strangulated galaxies continue to form stars using the available cold gas in the disk, which is not stripped. As a side note, if somebody is interested in protoclusters, I was also involved in the work of kinematics of galaxies in protoclusters using KMOS H-band observations of H alpha of 2 protoclusters from the Hyper-Subprime CAM Subaru Strategic Program. And you can look at the e-poster A5 of Asmus Böhm if you want to know more of that. So how do these enhanced metallicities compare to other studies at redshift 1.5? In a recent paper by Chartap et al., they looked with MOSFire at N2NH alpha of redshift 1.5 Kelvin. Here you can see the difference between the oxygen abundance in overdense region and field, and their result shows enhanced metallicities compared to field in their high density regions. This is an agreement with the enhancement index in metallicities compared to field galaxies from KMOS 3D found by our work, which is shown here as a best fit line. On the other hand, other studies, the gray symbols, they didn't find any enhancement in OH in denser regions, but they assume that all cluster members have similar densities. both are less than 0.5 R200 and are larger than 0.5 R200. So if one doesn't do a phase-space diagram and takes all galaxies also at R200 to R200 to be in the cluster, this weakens any underlying environmental dependence of the mass metallicity relation compared to studies where you look, for example, inside half R200 or in the overdense regions. So this brings me already to my conclusions. So we use KMOS H-band observations of N2 and H-alpha for XMM 2215 cluster galaxies, the redshift 1.5, selected from a phase-space diagram with many spectroscopic redshifts, which is unusual on these high redshifts. We got the galaxies which are inside R200, and they are distant from the cluster center. We found high metallicities of galaxies inside half R200 compared to field galaxies KMOS 2D, and infalling galaxies at similar redshifts. So we conclude that this is strangulation happening of cluster galaxies due to the stopping of the primeval gas inflow from the neutral gas reservoir, which would otherwise dilute the ISM and maintain their ISM metallicities at field galaxies values. But the cluster galaxies continue to form stars, albeit at slightly lower rates, using the available molecular coiled gas in the disk, which is not strict. Okay, thank you. Obrigado. Mulțumesc.